Welcome to episode 6 of the Ultrasonic Sensing video training series. This video will discuss the effects of the external matching components for the transducer to optimize ranging performance through hardware. In the event your transducer's performance needs additional hardware optimization, you must use external passive components called matching components. Matching components are typically more applicable to the transformer driver mode. Matching components such as a capacitor in parallel to the transducer, called a tuning capacitor, and or a resistor in parallel to the transducer, called a damping resistor, can help reduce the ring decay time or optimize the driver signal integrity. To understand how these components affect the transducer, consider that the transducer is mostly capacitive and can be modeled as a Butterworth-Van Dyke or BVD model. When plotting the impedance gain phase curves of a transducer across frequency, the BVD equivalent values can be extracted using curve fitting or by numerical computing environments such as MATLAB. The example shown is an analyzer plot of a 53 kHz transducer swept from 35 kHz to 70 kHz. The peak in the phase angle curve indicates the resonance center frequency of the transducer. The impedance curve corresponds to the reactive, inductive, and capacitive properties of the transducer across frequency. When the transducer frequency is at resonance, the current and voltage are in phase, resulting in a 0 degrees phase angle, which is observed as the midpoint of the rising impedance slope. Note, the BVD equivalent values of the transducer are not required to determine the matching component values. TI acknowledges that many users do not have access to an impedance gain phase analyzer. Capturing the BVD model is optional and is only useful if you decide to run simulations on your transducer. When using the transformer-driven mode, the equivalent circuit of the transformer introduces additional parasitics to the BVD model of the transducer. The transformer parasitic with the greatest performance impact is the secondary side leakage inductance. Recall, the transducer is a high Q component that resonates exclusively and most efficiently at a single frequency. For instance, a 40 kHz transducer cannot be driven at 30 or 50 kHz. Any drift from the resonant frequency yields a loss in the sound pressure level generated during burst. Most low-frequency transducers have a frequency tolerance of plus or minus 1 kHz, while high-frequency transducers have a frequency tolerance of plus or minus 10 kHz. When the series inductance of the transformer is introduced to the transducer, the resonant frequency between the transformer and transducer will likely result in a mismatch. To match the secondary inductance of the transformer to the resonant frequency of the transducer, a tuning capacitor is added in parallel to the transducer and can be approximated by the equation shown. Typical values for tuning capacitance ranges from 100 picofarads to 3 nanofarads. TI recommends using a capacitor bank to manually sweep and fine-tune the tuning capacitor for your specific transducer and transformer combination. If the tuning capacitor is too large in value, the resonance mismatch can actually be made worse. Some transformers are manufactured to be tuned to specific transducers and do not require a tuning capacitor. Higher frequency transducer and transformer pairs are less likely to require a tuning capacitor. The tuning capacitor is not required nor recommended for a direct driver solution because there is no parasitic inductance from a transformer present. The damping resistor is a resistor added in parallel to the transducer to help reduce the ringing decay time without significantly jeopardizing the driver strength of the long-range measurement. A damping resistor can benefit both the transformer-driven and direct-driven modes as a bleed-out resistor for post-excitation critical dampening of the ring decay energy. When damping resistor selection is optimal, it will have a negligible loading effect on the transducer during the burst and listen segments of the time-of-flight measurement. Thus, a damping resistor is always recommended. Optimizing the value of the damping resistor is a trial and error process of monitoring the ring decay and object SNR in a single time-of-flight measurement. The optimal value is dependent on your performance requirements. Given the value of the damping resistor ranges from 500 ohms to 25 kiloohms, TI recommends using a potentiometer or resistor bank to sweep and fine-tune the damping resistor for your specific transducer and transformer combination. Transformers are typically fixed in value, but variable coil transformers are available to enable tuning of the secondary side inductance of the transformer to better match the transducer's resonant frequency without the need for a tuning capacitor. The tunable transformer's value can typically be adjusted by the top notch of a screw-type control. The figure shown compares the ring decay profile of the transducer before and after the variable transformer is tuned. Though the variable transformer eliminates the need for a tuning capacitor, the need to manually fine-tune each transformer at mass production can increase line calibration time and cost per sensor. For this reason, a fixed transformer and tuning capacitor option tends to be more popular. In summary, only use a tuning capacitor with the transformer-driven solution when applicable, and try to use a damping resistor for every solution.